All right, so this chapter is about gravitation. Okay. I'm just going to go over the punchlines from most slides, okay? So these are the topics we'll study. We'll study Newton's law of gravity, okay? All right, so here's a big picture view of it. Newton's law of gravity, Mr. Newton came up with this 1687, that's 40, 70, 340 years ago. Okay? Now this law is good for weak gravitational fields. Okay, and so we won't worry about this. This also for objects that are not moving close to the speed of light. So anyway, this law is good for weak gravitational fields, the gravitational field of the Earth and so on. Okay, so if you wanted to go near black holes and stuff like that, to describe phenomena there, you'd have to use general relativity. This is a refinement of Newton's law of gravity. So for strong fields, you would have to use general relativity. Yeah. It's much harder, but so if you want to, talk about black holes and stuff, you have to use that. Now, this is not the final word. The final word is really a quantum theory of gravity, and you would need that to talk about how the Big Bang happened and near events happening right after the Big Bang and stuff like that. You need to use that. Okay? So we're talking about weak field gravity, and Newton's laws are good enough for that. So, by the way, so general relativity, this in the weak field, it reduces to that, and in the absence of gravitational field, general relativity reduces to special theory of relativity. Anyway, so that's a big picture. So here's Newton's law of gravity. What Mr. Newton said was, every object attracts every other object in the universe. The magnitude of the force between two objects is, so this object attracts this object, Mr. Newton says, and this object in return attracts this object. So, for instance, if this object attracts him with a force of 100 pounds, what does this guy do? I'm sorry? This guy attracts him with a force of equal magnitude. Okay, so that's Newton's third law. Okay. All right, well, how do we calculate the magnitude of this force? The magnitude of the force is given by this formula. Mr. Newton came up, this is Newton's law of gravity. That is the universal gravitational constant. That is the same constant no matter what two objects you're talking about. So that's why it's called the universal constant. Times the product of the masses divided by the distance squared. And the distance is measured from the center of gravity of the two objects. Okay. Now, so for instance, what this formula says is, if you double the distance between these objects, the force reduces by a factor of 4. Okay. If you double the masses of each object, then the force increases by a factor of 4. Okay, and so on. So it says all of that. Okay, it turns out that in nature there are 4 fundamental forces: the strong force, the electromagnetic force, the weak force, and gravity. And gravity is the weakest of those 4 forces. And that's because this constant is very small. If you want to make gravity stronger, you just make this constant stronger. Okay? So the universal constant is given by that. Okay. Units are Newton meter squared divided by kg squared. In fact, this constant is currently in all of physics is the least accurately measured constant. Yeah. Newton came up with this law in 1687, and this constant was not measured till 1800s almost. 100 years after Mr. Newton came up with this law. Yeah. All right, so again, the force, Newton's law of gravity is m1, m2 divided by r squared. Okay, and we just said that this constant is very small. And so if you want this force to be large, okay, at least one of the masses has to be large. So for instance, if you calculated the force between these two things, these masses are not large. And because this constant is small, this force is very small. So the force between these two guys is about 10 to the minus 7 newtons. That is the weight of this period if it was all made of carbon. Okay, now on the other hand, the force between this guy and this object, that's strong, because the mass of this object is quite large. Okay. So the force between the earth and the person is 1,000 newtons. And the force between the earth and the dog is 10 billion times weaker. Now the force of gravity exists between all objects. It exists between galaxies and stuff like that. And as a consequence of these guys, none of these objects are at rest in the universe. Everything is moving. Yeah? And in fact, we are on a collision course with the Andromeda galaxy. So the collision will happen in another 4 billion years. All right. Like I said, Mr. Newton gave us this law of gravity in 1687. And this guy was not measured till 1800. Okay. Mr. Cavendish measured this. Yeah. And so this was an important experiment. I'll briefly describe this to you. And then we'll understand why this was called weighing the Earth experiment. Yeah. So this is what is called a torsional pendulum. Okay. So what you do is you take a stiff wire, stiff metal wire, have a rod, and if you have two weights, or you could hang a disc or whatever, and this is a torsional pendulum. If you twist this wire, what do you think will happen? So you have a wire like this, you attach an object here, and you twist the wire and let go.
The object will return to its original position with an opposite rotation.
It'll return to its position. It will oscillate. Okay, and the stiffer the wire, okay, stiffer the wire, what do you think will happen to the oscillations?
Faster.
The frequency will be higher. Okay. Stiffer the wire, harder it is to turn through a certain angle. Okay, so from how much it turns, you can calculate the force needed to. Okay, it's a torque, and the torque is force times the distance. Okay. All right, so here is the experiment. So here is this wire, torsional pendulum, and you have these. So this pendulum is, and you have these two weights, and it's hanging there. And then what you do is, so you bring these two heavy masses. So here's your torsional pendulum hanging, this heavy mass is down there, and then you raise it up to that point. Now, what is this heavy ball going to do to this little ball? It'll attract him. Okay, and this will attract this little ball, and this heavy ball will move there. Okay, you measure this angle, okay, the angle of the twist, and so you know the torque that was applied to this, and you can calculate the force between these objects. The force between the objects is, again, Gmm by r squared. You know the distance between the objects, you know their masses, you know the force from the angle of twist, and you can figure out G. Okay. So that's how Mr. Cavendish measured this, measured G. Okay. And why do we call this weighing the earth? Well, okay, so here's why we call it weighing the earth. So you guys have done in lab, what is the acceleration due to gravity?
9.8 meters per second squared.
Yes, okay. So you measured that quite easily. So the force on an object near the surface of the earth is Gmm divided by the radius of the earth squared, because you know the distance between this object and the center of the earth is the radius of the earth. All right, the mass of the object cancels. You have measured G. We've known the radius of the earth for about 2,000 years. The Egyptians measured that. Yeah. And now, in 1800, you measured this guy. So suddenly now you can calculate the mass of the earth. Okay. So from this equation, you see that mass of the earth is G times the radius of the earth squared divided by G. So the instant you measured that, you got the mass of the earth, because you knew G and you knew R from a long time ago. Okay. So in 1800 is when, one evening on 1800 is when we knew the mass of the earth. Yeah. Now this opened up all kinds of, opened up a can of all kinds of worms. So for instance, okay, if you go outside and pick up a fistful of dirt and calculate the density of the dirt, the density of that dirt is about 2 grams per meter cube, centimeter cube. Okay, about 2.5 times the density of water. Now that you have the mass of the earth, you can calculate the average density of the earth. The average density of the earth is just mass of the earth divided by 4 pi by 3 r radius cubed. And the average density of the earth is 5.5 grams per cc. Okay, for the dirt outside, it's 2.5 grams per cc. What does that tell you? So right away, that tells you that if you go deeper inside the earth, the density must be higher. Okay. So eventually we found out, so here's the density profile. At the center of the earth, the density is 14 grams per cc. And on the surface, it's about 2.5 grams per cc. Okay. And so here's a picture of the internal structure of the earth. Now this picture is only about 60, 70 years old, or maybe 50 years old. Okay. So we didn't know this 100 years ago. Well, how do we know the structure of the earth, the internal structure of the earth? Okay. Okay, a wave will travel in a straight line. Okay, so a ray of light will travel in a straight line. Is there any time it'll bend? Will a wave not travel in a straight line? Does a light ray bend anytime?
Going through glass or water.
Yeah, so a wave will bend when it goes from one medium. So let's say this is air and this is glass. Okay. A wave will bend when it goes from one medium to another if its velocity changes. Okay, this is called refraction. So if it's going from this medium and encounters the second medium, and if it's going slower in this medium, then it'll bend towards the normal. If it's going faster in this medium, then it would go in that direction. Okay. And from the bending, you can calculate the velocity in this medium. From the velocity in this medium, you can calculate the properties of that medium. Okay, and this is true for all waves. So here's an earthquake, and these are earthquake waves traveling through the medium. Okay, so an earthquake happens here. You have seismometers all around the world, and you can collect data from hundreds of thousands of earthquakes. You put together data from hundreds of thousands of earthquakes, gotten all this data, reconstructed these paths. From these paths, you know the velocity profile, from which you know the property of that medium. So this picture of the Earth, the internal picture of the Earth, is very new. It's only about 50 years old. Needs a lot of computing power. Okay. So only since high power computing has come about, since then is when we have this picture. All right, so here's the Earth. Here's the International Space Station. The International Space Station is flying about 300 miles above the surface of the Earth. Okay. Now, what this slide says is, if the object is outside of a spherically symmetric object, the force of gravity on this, once you're outside the object, would be the same if you just turn this object into a point object. Okay, so what we are saying is the orbit of the International Space Station would not change if you somehow turn the Earth into a black hole, which would be a tiny object. Okay? Doesn't care. If the sun turned into a black hole, our orbit would not change. Okay. So the gravitational force exerted by a finite size spherically symmetric mass distribution on a particle outside the distribution is the same as if the entire mass were concentrated at its geometric center. Mm-hmm.
When calculating the force of gravity while standing on Earth, do we still treat Earth as a point mass?
Yeah, you can treat it as a point mass. Yeah.
Because we're technically outside of the
Yep,
sphere.
exactly. So that's the point. Mm-hmm. Yeah. So to calculate, yeah. All right. So our solar system has multiple objects. Yeah. So for instance, if here are three objects, if you wanted to calculate the force on this guy due to these two guys, what you do is calculate the force between these two guys as if this guy is not there. So you calculate this force, and then calculate the force between these two guys as if that guy is not there, which is that force. And the net force on this guy is just the sum of those forces. And that's the superposition principle. Yeah. Again, you guys have measured g, acceleration due to gravity, which is 9.8 meters per second squared. Okay? But that is on the surface of the Earth. Okay. What about if you were here? Well, if you're here, okay, the gravitational force on you, mg, is equal to g, mass of the earth, times your mass divided by r squared, where r is this guy. Okay. This distance is radius of the earth. Okay. So g far away is g. So by the way, the mass cancels. So g far away is gme divided by r squared. And now we'll measure this g as radius of the earth plus h. Okay, the height above the surface of the earth. Okay. So g is re divided plus h. Okay. And then you can pull out re, and you get a square, gme re square. And this quantity is g is 9.8 meters per second square. Okay. G naught equal to 9.8 meters per second square equal to g mass of the earth divided by the radius of the earth square. Okay. And so this is 9.8 meters per second square. So g at an arbitrary distance r is 1 divided by 1 plus h, the height above the surface of the earth, divided by the radius square. And now if, by the way, do you know what the radius of the earth is?
6,000 kilometers?
So very good. Radius of the earth is 6,400 kilometers, equal to 4,000 miles, about 4,000 miles. Okay, so if you, let's say, are 10 miles above the surface of the earth, 10 divided by 4,000, this is essentially 0. Okay, so if you're at heights that are small compared to the radius of the earth, then g is essentially 9.8 meters per second. G changes if you jump, let's say, 1,000 miles. Now that is comparable to the radius of the earth. Okay? So for instance, at an altitude of 1,000 kilometers, g has reduced to 7.33 meters per second squared. Okay. All right, so this gives you g as a function of your altitude above the surface of the earth. Yeah. Here's a picture. And again, this is a vector field. The acceleration due to gravity is a vector, and it points towards the center of the earth. And the further out you are, the magnitude decreases. Okay. All right, so here's an interesting idea. Yeah. So, oops. Let's say this is the earth, and let's say now it's not rotating. Okay? And you stand on the earth. What is the earth doing? It's pulling you with the force of gravity. Why aren't you falling down? Why aren't you going through the earth? Because the ground is pushing you back with an equal force. The normal force is what you call your apparent weight. Okay? So why does your hair feel heavy? Because your head is pushing up on the hair, and that's okay. So that normal force is what's pushing you up. Okay? All right. Now what we're going to do is we are going to go to the equator. All right. And now let's make the earth spin. Okay. So, by the way, the earth, the radius is, the earth at the equator is going at 1,000 miles an hour. Okay. The radius of the earth is 4,000 miles. 2 pi is roughly 6. 6 4 is 24. It's taking 24 hours, so 1,000 miles an hour. Okay. So you're going at a constant speed, 1,000 miles an hour. Are you accelerating? I'm sorry?
At a constant speed?
Yeah, going at a constant speed.
The acceleration is zero.
So you're accelerating towards the center while you're spinning.
Why are you accelerating?
There's centripetal acceleration, otherwise you'd be thrown off or tangential.
But why are you accelerating? Why is it changing?
Because it will change direction.
There you go. That's what I was looking for. All right, you're accelerating because your velocity direction is changing, and that's the centripetal acceleration. And the centripetal acceleration is v squared divided by r. Okay? You're accelerating. So, Mr. Newton tells us that if you're accelerating, there must be this much force acting on you. Okay. Well, where is this force coming from? Now, there are two forces acting on you. Okay, so you need this much centripetal force. Well, where is this force coming from? Here is the force of gravity, and there is the normal force. Okay, so when the Earth was not spinning, the normal force was equal to that because the net force on you was zero, because you were not accelerating. Now suddenly you gave the Earth a spin, gravity didn't quit on you, but because you needed the centripetal force, this force decreased. Did you guys understand that? As soon as you spun the Earth, now your apparent weight is decreased. So I'll tell you a very cool fact. Do you guys know how fast the space station goes around the Earth? How long does it take for the space station to go around the Earth?
90 minutes.
Very good, 90 minutes. Okay, and you feel weightless in there. How long does it take for the Earth to spin once?
A day.
Huh?
A day.
A day. 24 hours.
Yeah.
If you made the Earth spin once in 90 minutes, this guy would go to zero. You would feel weightless on the surface of the Earth. Okay? In fact, if it was spinning in 90 minutes an hour, you could walk off and you could walk off into space. All right. All right, so, see, there's the force of gravity, and there's the normal force, okay? So as long as the Earth is spinning, then this has to be less than that, you know? And the effective gravity, so we can say the effective gravity is G minus that, okay? On the poles, you're not moving. Okay, so if you lived on the poles, then your apparent weight is equal to the force of gravity. Only at the equator you weigh the least, your apparent weight is the least. Yeah? And in fact, for a rotational speed, you weigh about 0.35% less at the equator than at the poles. So if you weighed 100 pounds, if Santa Claus weighed 100 pounds, if you brought him to Ecuador, he'd weigh 99.65 pounds. Yeah. Okay, so here's another very interesting thing. All right, how's this? Let's say this is building. Is it perpendicular to the surface?
Yes.
Oh, you know, it's not. Okay, so we'll show you that buildings constructed in the northern and southern hemispheres are not perpendicular to the surface. Okay, so if you build a building in the northern hemisphere, in fact, it's tilted towards the North Pole, and in the southern hemisphere, it's tilted towards the South Pole. Okay, so let's show you that. For the tallest buildings, this represents a deviation of a few feet at the top. So, for the tallest building in this room, I'm disoriented. Okay, this way is north. So in this building, buildings are tilted towards the North Pole. And if you went to the southern hemisphere, that'd be tilted towards the South Pole. All right, so let's understand this. Okay, so let's say you're here on Earth. The Earth is spinning. So this object is going in a circle like that, where that is the center. Okay, this object is going in a circle, and you need a centripetal force in that direction. Okay, there's a centripetal acceleration. Okay, so let's look at this object. Here is so when you're building a building, this here is a plumb bob that's attached to the ground. Okay, so here is this object that is going in a circle like that. And what do you need for it to go in a circle? You need a centripetal force in this direction. Okay. All right, what are the forces acting on this guy? The only two forces acting on this guy are the force of gravity in this direction and this spring pulling him back. And those two forces, this force and this force, must add up to give you this force. So you guys see that this force is in that direction. There is the force of gravity, so this force has to be in that direction. That this force that the plumb bob is exerting, it can't be in that direction, because if it were in that direction, then you can't get a net force in this direction. Okay, so let me redraw that. So this is the spring force that is exerted. So the spring force has to be like that, and here's the force of gravity, mg. This combined with that gives you the centripetal force. This is highly exaggerated, but here is the force of gravity acting on him. There is the spring force acting in that direction, slightly different angle. Okay, there is the force of gravity, and these two add up to give you that. And you see, that's the direction in which you're building your buildings, in the direction of the plumb bob. So if you build a building anywhere in the northern hemisphere, it's leaning towards the North Pole. The only two places where the buildings are vertical, only places where the buildings are vertical are Ecuador, the North Pole, and the South Pole. Yeah. All right. Now, Mr. Newton was a very smart guy. Okay, so what he proved was the following. So let's say this is a basketball. And if you find yourself inside the basketball, what Mr. Newton proved was, what do you think? Will there be a force of gravity on you?
Yes.
Okay, so that's what we would all answer. So if you were here, this basketball attracts you in this direction, this piece attracts you in this direction. Well, this piece is smaller than this piece, well, but this guy is closer than that guy. And it turns out what Mr. Newton proved was the force of this guy will cancel the force of this guy. So if you are in a shell, no matter where you are in the shell, inside the shell, as long as the shell is uniform, the force of gravity on you is zero. Yeah, not an easy thing to prove, but Mr. Newton proved it. Okay, so if you are in a uniform shell, the force of gravity on you is zero. All right, well, why does that matter? Okay, so let's say here the Earth. The Earth is not uniform density, but let's say to approximation, it's of uniform density, okay? So let's break it up into shells, okay? You know, if you were on the surface of the Earth, what is the force on you? M times G, which is G is 9.8 meters per second squared. If you were here, all this guy is not attracting you. The force of gravity on you is just because of this guy. How about if you were here? All this stuff is not attracting you. Only the force of gravity on you. What if you were at the center of the earth? What is the force of gravity on you?
0.
0. Very good. Okay. So here's just a fun thought experiment. Okay. So let's say we build a tunnel through the center of the earth. I'm sorry? By the way, just to give you an indication, this is almost impossible. What is the radius of the earth? 4,000 miles. The deepest hole we've dug is 4 miles. That's 0.1%. So we barely scratched the surface. Okay? So this is impossible. Ain't going to happen. But let's say we did this. What you find is the force on the object as you go down this tunnel is proportional to r, the distance from the center. At the center, you already saw that r would be 0, the force on you would be 0. Okay? And if you remember this from one of the previous chapters, this is exactly like this force, like the force on a mass attached to a spring, versus k is the spring constant. Here would be the spring constant. Okay, so I don't know if you remember this, but let me draw this, guys. So here's a mass attached to a spring, and if I pull this mass to the side and let go, what will happen?
Go back to the equilibrium.
If I let go, what will happen?
It'll go back to the original, then compress slightly.
It will oscillate. Okay? So let me show you. All right, so we attach a mass to the spring, and you stretch it and it'll oscillate like that. Okay? And we'll do an entire chapter on this. It'll be going fastest at the equilibrium point and so on. Okay? So let's say you build this tunnel and the force on you is exactly like that of a spring, the force on a mass attached to a spring. So what do you think will happen if you stepped into this tunnel?
Assuming it's in a vacuum, you'd fall to the center, accelerating, and go all the way back up to just shy of the other side of the Earth, and repeat.
Exactly. You would oscillate just like that mass. And here's the very neat part of it. The fastest you'll be going the fastest at the center, and you'll be going at about 18,000 miles an hour. And this is exactly the speed of the International Space Station.
Is that a coincidence or just?
No, because they're related, and we'll talk about that. So this is very cool. The period of oscillation, the time for one oscillation, is 90 minutes, which is the time taken to orbit by the International Space Station. So in chapter 15, you'll study uniform circular motion is a combination of two simple harmonic motions. Yep. All right, so very neat. Okay, we'll skip this. So there's the period of oscillation in that tunnel. Okay. You guys understanding this? Am I going too fast or? All right, you guys remember the formula for the gravitational potential energy?
MGH.
MGH. Okay. where h is the height above the surface of the earth. Okay. Now, okay, let's see. This formula is good as long as g is constant. If g is not constant, this formula is not good. Well, how high do you have to go before g changes? Yeah. So you have, I'm sorry? Yeah, so you have to go large distances, large compared to the radius of the earth. Radius of the earth is 4,000 miles, and even if you jump 40 miles, that's only 1%. Now you jump 400 miles, that's 10%. Okay? So you have to jump at least 400 miles before this guy is no longer good. Okay? Starts becoming bad. All right, well, what is the accurate formula? So we'll give you the accurate formula. Here is the accurate formula. Okay. Well, why didn't we give that to you before? Because this guy is a pain in the neck to use. Okay? Yeah, this gravitational constant is a small number. You need to measure the distance from the center of the earth and stuff like that. Okay? If I climb the top of this building and then you ask me to give you the distance from the center of the earth, that's, yep.
A few slides ago, on one of the equations, there was a r with a caret on top of it. Just
Mhm.
wondering what that caret, or what that r caret is for.
Okay. Okay, so this is the Cartesian coordinate, and what is I hat?
Oh, that's our x-axis.
That's the unit vector pointing along the x-axis. J hat is the unit vector pointing along the y-axis. Okay? And those are useful. Okay. Now, this Cartesian coordinate is not always the most convenient to use when okay. You use different kinds of coordinates based on the problem that you're solving. Okay? So it's like saying that if you're in North America, English is a good language to use. No. If you're in South America, then Spanish is a good language to use. Okay? So depending on the problem that you're solving, you use the appropriate coordinate system. Okay, so now there's something called spherical polar coordinates. Okay, so if this is a point, this is the radial distance. R hat is a vector in this direction. This angle is theta, and by the way, the physicists and mathematicians define it differently. There's the projection, and this angle is called phi. So the coordinates of this point, the address of this point, this is the address of this point in Cartesian coordinates, and the address of that point, r, theta, phi, are in spherical polar coordinates. Yeah. R hat is a vector in this direction, theta hat is a vector, unit vector in this direction, and phi hat is a vector in that direction, unit vector in that direction. Yeah. All right, so we'll come to a problem in a second where Cartesian coordinate is not the language to use, spherical polar coordinates is the right language to use. Okay? So, here we go. Okay? So, if you wanted to calculate, so what are we doing here now? So this was, what is this guy?
Potential energy due to gravity function.
Yeah, the potential, gravitational potential energy. And when is this fella good?
Close to Earth's surface.
Yeah, when g is constant, very good. When you're close to the surface of the earth, this guy is good. Okay, let's say you suddenly decide to jump 400 miles, this guy is no longer good. Okay, you want to go on an interplanetary journey, then this fellow is no longer good. Well, how do you calculate the correct expression? All right, it turns out that the work done by a force, work done by a conservative force, and this is the definition that we gave in chapter 6, so whenever, okay, is equal to negative of the change in potential energy. Okay. What happened? Oh, no, I'm just kidding. Okay. The work done by a force is this line integral. Okay. Now, for this particular problem, okay, this has spherical symmetry. What you want to do is, see, the force only depends on the radial distance. What you want to do is this integral you want to do, you want to do this line integral not in Cartesian coordinates, you want to do it in spherical polar coordinates. Okay? You could do this line integral in Cartesian coordinates, the problem would be very hard. Okay? So I'm just going to, okay, so let's see. I'm going to copy this fellow, and I'm just going to show you the result. Okay. Whoa. Why did it do that? Okay. So this is equal to, the force is minus GMM divided by R squared R hat. That's the force of gravity on that particle. Okay, the force due to this mass on this guy. And in spherical polar coordinates, dr, the small displacement is given by dr, that's the distance in, along the radial direction, r hat plus r sine theta, d theta theta hat plus, again, r d theta and r sine theta d phi hat. Okay, so when you do Calc 3 and when you do spherical polar coordinates, you'll learn this. Okay, so what this is saying is a small displacement, let's say here, so there is a small displacement, dr hat. This portion is in the radial direction, this portion is in the theta hat direction, and this portion is in the phi hat direction. Okay. So when you're doing this integral, so you do this, and again, r hat is 1, r hat dot theta dot is 0, r hat dot phi dot is 0. Okay. And so this integral reduces to minus GMM over r squared dr. Okay, from r initial to r final. And this integral is very easy to do. It's like 1 over x squared dx, okay, which is equal to 1 minus x. Okay. All right, so again, the point of the story is when you're solving a problem, you want to use the appropriate language to solve the problem. Okay. So spherical polar coordinates is where you do this. Okay, so going back to that, so that integral is done, and which is equal to this. So you can see that, so you can write this as minus GMM by R final minus GMM by R initial. No, minus a minus, which is plus, minus a minus. Okay, so this guy is U final, and this guy is U initial. Okay. So, again, U, the gravitational potential energy is mgh, as long as you're close to the surface of the Earth, and this guy doesn't change. When you jump high and far, and you want to get an accurate expression for the gravitational potential energy, it is this expression. It's minus g mass of the earth times your mass, and r is the distance of where you are from the center of the earth. That is r. Okay. So that's the more accurate expression. And we'll use this as long as we can get away with that, because this guy is a little pain to use. Okay? But if you're going to the moon, then you have to use this guy. Okay? All right, now let's put together a solar system, a bunch of particles. Okay? You want to calculate the potential energy of this system. What you do is the potential energy of this pair plus the potential energy of this pair plus the potential energy of this pair. Okay? So the total potential energy of the system is the sum of the potential energies of all the independent pairs. Okay? And that's that. All right, we'll just do this few slides and then take a little break. Okay. So let's say this is the Earth, and you throw a baseball up. Okay, you throw the baseball, it goes up and then comes back. You throw it faster, what will happen?
It'll reach a higher height and then come back.
Can you throw it so that it never comes back?
Theoretically,
Okay, and that is called escape velocity. Okay. It turns out that you can, if you throw it at 11 kilometers per second, so let's be more precise, 11.2 kilometers per second, then it'll never come back from the surface of the Earth. Well, if you were higher up, you wouldn't have to throw it as fast, let's say 10 kilometers per second. So escape velocity from any object is the velocity at which you need to throw so that it never comes back. Yeah. What is the fastest any object can go?
speed of light.
Speed of light. From the surface of a black hole, this escape velocity is c. Nothing can escape, not even light. That's why it's called a black hole. Okay. All right. So the escape velocity from an object, from the surface of the object, is given by that. Okay. And the escape velocity, so if you throw, and this works out to 11.2 kilometers from the surface of the Earth, you can put these numbers. So if you throw the object at 11.2 kilometers per second, it'll not escape. We're neglecting the friction due to the atmosphere. And that velocity is independent of the direction. Okay. Any direction you throw, it'll escape. Okay. So here are the escape velocities. And of course, the escape velocity, this is from the surface of the Earth. Escape velocity, so this is the general expression from any object from any distance. Okay. So larger r is, lower the escape velocity. So the escape velocity from the surface is 11 kilometers per second, but if you're further away, the escape velocity decreases. Okay. So here are the escape velocities from the surface of the Earth. It's 11.2 kilometers. From Jupiter, it's 60 kilometers per second. Okay. From the surface of the Sun, it's 600 kilometers per second. Okay. Now, you have to worry about this kind of stuff because, we did go to the moon, and then you had to escape from the moon to come back to Earth. So you'll need to know how much fuel you need and stuff like that if you want to come back. Okay. By the way, do you guys know what do we have in our atmosphere? What's the atmosphere content?
percentage,
Yeah,
80-20, nitrogen, oxygen, other stuff.
so nitrogen is 78%, oxygen is 21%, and other stuff is 1%, okay? You know, 92% of the atoms in the universe are hydrogen. 8% of the atoms in the universe are helium. All the other stuff is less than 1%. We have none of this in our atmosphere. What's going on? You go to Jupiter, you'll find plenty of that.
Gravity not strong enough?
There you go. You go to Publix, buy a helium balloon, and let go of the helium. All this guy will escape to space. Okay? So, if the average velocity of a gas molecule is 1/6 the escape speed, so if this was 12, if the average velocity of helium would be less than 2 kilometers per second, it would escape. Okay? At the moon, the moon has no atmosphere because 1/6 of that is 0.4 kilometers a second. At the temperatures of you experience on the surface of the moon, you release any gas, it'll escape. Okay? All right, so that kind of stuff is important to calculate all that kind of stuff. All right, we'll pause for 30 seconds.